Engineers propose the most audacious tropical mega-project, a 250-kilometer elevated bridge soaring over the Amazon. Priced at $25 billion, this overland corridor will link isolated Manaus directly to the Atlantic Ocean. Built 40 meters above ground, the bridge remains completely untouched by extreme seasonal rainforest floods. Spanning 250 kilometers, it will become the world's longest continuous over-canopy viaduct ever constructed.
Electric trains traveling at 250 kilometers per hour will cross the basin in under 2 hours.
Electric road trains replace slow barges, cutting cargo transport times from 14 days to 3 hours.
Friction pile foundations driven 100 meters deep anchor every bridge pier securely in soft mud.
Overhead launching gantries assemble prefabricated steel bridge modules, ensuring zero land clearing during construction. Solar road panels and pylon-mounted micro wind turbines generate megawatt electricity along the entire structure. An 800-meter cable-stayed main span clears the river, allowing cargo vessels to navigate freely underneath. AI digital twins monitor structural strain and wildlife movement, preserving 98% of natural canopy. Phase 1 focuses on deep alluvial soil stabilization, friction pile driving, and over-canopy viaduct engineering. Geotechnical teams drill 120 meters deep, mapping soft alluvial clay down to bedrock. Clusters of 3-meter-wide steel friction piles transfer massive bridge loads into deep, compacted clay. Heavy hydraulic pile hammers drive giant steel casings, operating at double speed during dry season.
Subscribe now and comment below on what tropical mega engineering project we should cover next.
Deep cement mixing rigs inject binder slurries, transforming soft mud into solid foundation columns. Prefabricated concrete caisson caps bind pile clusters together, creating solid footings above flood levels.
Self-climbing hydraulic formwork constructs 50-meter concrete pylons upward, rising high above the green canopy.
Aerodynamic diamond pylon shapes divert storm wind gusts, eliminating structural sway during equatorial squalls.
Submerged bubble curtains dampen pile-driving shockwaves in river waters, protecting pink Amazon dolphins. Piers extend across miles of floodplain wetlands, built on slender columns to allow free water flow.
Heavy basalt armor blocks placed around pylon bases prevent riverbed scour caused by swift currents.
Phase 1 is complete. Next, we examine top-down viaduct launching, steel box girders, and spans. Phase 3, over-canopy viaduct launching. Overhead gantries push prefabricated steel box girders forward safely.
Galvanized stay cables coated in high-density polyethylene withstand 90% humidity and extreme ultraviolet rays. Double-deck steel trusses carry a 4-lane highway on top and a high-speed railway below. Automated welding robots join steel box girders in mid-air, creating a continuous aerodynamic beam deck. An 800-meter main cable-stayed span crosses the river, providing 70 meters of air draft. Specialized high-durability epoxy asphalt paving protects the steel deck against heavy loads and heat. Modular finger expansion joints allow the steel bridge deck to expand safely during temperature shifts.
Transparent, porous wind barriers line the deck, dampening crosswinds to keep high-speed traffic stable.
Enclosed utility corridors inside the box girder carry high-voltage lines and fiber-optic communication trunks. Kilometer after kilometer, the elevated steel deck forms an unbroken ribbon soaring above the forest. Solar-powered environmental sensor posts monitor air quality, canopy humidity, and animal activity continuously. Phase 3 is complete. Now explore intermediate eco-hubs, wireless charging, and automated transport. Phase 4, eco-hubs and automated transit. Service islands house solar microgrids, battery banks, and emergency crews.
Autonomous electric road trains cruise along dedicated freight lanes at 100 kilometers per hour. Electric bullet trains transport thousands of passengers daily across the Amazon basin in comfort. Dynamic wireless induction coils embedded in the surface charge vehicle batteries continuously while driving. Pylon-mounted wind turbines and rooftop solar arrays generate gigawatts of clean power along the route. Utility-scale lithium battery storage banks store surplus solar energy, powering the highway throughout the night. Robotic cleaning drones patrol the deck, using high-pressure air blasts to keep panels operating efficiently. Smart LED lighting systems adjust brightness dynamically based on vehicle traffic, cutting energy consumption. Automated emergency barriers and fire suppression systems respond instantly to accidents, maintaining continuous safety. Toll revenues and green freight tariffs ensure full capital cost recovery within 15 years. Oil-separating drainage scuppers filter rainwater runoff completely before discharging clean water into tributaries. Phase 4 is complete. Next, we examine regional economic transformation, trade logistics, and legacy. Phase 5, Global Legacy. The bridge connects Manaus's industrial free trade zone directly to Atlantic routes. Freight transit times drop from 14 days by riverboat down to 3 hours by high-speed rail. Automated smart customs gates process freight trucks in seconds, integrating the regional hub into international chains. Annual trade expansion across South America is projected to reach $40 billion within 10 years. Elevated access stations provide indigenous communities with medical and educational transport links without clearing land. Satellite data confirms 99% forest canopy preservation along the corridor, proving sustainable infrastructure. Clean solar electric maintenance boats service river pylon footings regularly, maintaining foundation integrity with zero leaks. Civil engineers worldwide study Brazil's Amazon Bridge as the masterclass prototype for zero deforestation transit.